Okay, good morning. So let us start the lesson officially today. I will not teach that much, but I want to give you a little bit of introduction. What is this course about? Uh, so the topics that we will cover here is methods of proof. Yeah, let me write proof methods. Of course, I mean in mathematics. And then we can talk a little bit about logic, and then number theory, and set theory, and combinatorics, and then differential equations. Usually this is a little bit strange to have it in this course because these parts are part of the mathematics which is called discrete mathematics. So mainly we want to, for the very first part of the course, we are dealing with discrete mathematics, which is a new type of mathematics for you if you don't already know about this. But differential equation is more or less math 4. So it is part of another part of mathematics usually called mathematical analysis or just differential equations, yes? So this differential equation has moved from math 4. In math 4 we had one section on differential equation that is now eliminated and has moved to differential equations here, and it has been extended. So the one that you have in this Origo book is not complete. By that time, I will probably find a way to give you extra material that we need. It's a very long section that is been added to this differential equations part. In this chapter, of course, we need a little bit of math 4 that we haven't covered yet. But when we reach to this point, we have already covered everything we need to start this. Okay? But this is the same type of mathematics that you are used to up to this point. But these are not that type of mathematics, probably you are familiar with that much. So somehow people find it more interesting, sometimes people find it more hard. Harder. It depends the way that you think, okay? So the good point about discrete mathematics from students' point of view is that it does not need any prerequisites at all. So it doesn't matter if you have forgotten whatever you studied before or what. Usually you don't need anything to start. Of course, anything is exaggeration. You need to know a little bit of mathematics, but not that much. In principle, I could have started teaching discrete mathematics when you are in the first grade. That level of mathematics that you know from previous studies in Grundschule, in principle, is enough to teach this. Okay. This is the good point. The bad point about that is there is no general rule to solve the problems. So for example, in math 4, you learn the notion of derivative, and then you know how to find the derivative of a function. Then what I can do, for example, if I want to make a Hardik problem, I give you a little bit complicated function. Then you have one rule or a set of rules. You try to break that problem into pieces and use those rules so that you can solve the problem. But that idea is gone here. So it means that you can probably solve the first problem, but there is no guarantee that you can solve the second problem, because the second problem is a completely new problem. So you have these dynamics, you have to be able to think creative. Otherwise, it becomes hard. So that is the weakness from a student point of view. For me, that is the beauty of this, because every time you think a new problem, and if you like mathematics, you will enjoy that. Okay. So this is the hard part of this course, and then the simple part is that you don't need to remember anything from your previous studies that much. Okay? Today, let me try to give you a little bit of flavor what you expect, you might expect. Might be it is easier for you to understand what I said by bringing you some examples. Okay? So a problem that you might expect, for example, in number theory, let me ask you this question, okay? Do you think there are integers? So integers are these numbers. So the set of integers in mathematics is denoted by z, and they put another extra bar here to denote that this is the set of integers, and this is the set containing heltal, whatever you say in Swedish, but in English we say integers. So it's -3, -2, -1, 0, 1, 2, 3, up to etc. Okay. So my question is that if I give you this equation, x plus y equals to z, how many variables you see? 3, x, y, and z, yes? And do you think you can find numbers, can you find a triple of numbers x, y, and z from this set that satisfies this equation? Yes? For example, can you give me an example? Can you choose 3 numbers x, y, and z coming from this group of numbers so that this equality holds? Yes? Yeah, for example, you can choose 1, 2, and 3, and it works. Another example, can you involve negative numbers as well here? Yes? -2, 2, 0, yes? If I add them. And these numbers, you have respected what I said. You brought them from here. Yes? So, now another question. How many triples you expect you can find? How many different triples? 2 triples are said to be different if they at least differ by one of the components. So how many, intuitively, okay, how many triples you expect that you can be able to find, yes? Infinitely many, yes? Do you agree? Do you feel that or not? Do you feel that you can play around with these numbers infinitely many, so in infinitely many ways, yes? For example, you can choose these two, any numbers that you like, for example, 1 and 2, and then you choose this one to be the sum. I can choose -5 and -7. I can choose it what? -12, yes? So in how many ways I can choose 2 numbers from this infinite list? Infinitely many. And then I add them, it becomes a number, then I have my triple. Is that clear? Okay. So this is the way that mathematicians think. So when they solve this problem, and when they want to sleep, they don't have any problems, they make a problem for themselves, okay? That's the idea. I just want you to, this is a little bit different from science, yes? And so, for example, I don't know, in science, you have an illness, okay? You start working and solving the cure for that illness. If you're not ill, you even don't think about it, okay? But in mathematics, this is the other way around. If you don't have any problem, you start thinking to make a problem for yourself. Okay, that's the attitude. Okay, so and that's something that comes to the mind of a mathematician is to generalize the ideas and rules. Okay, so when you say here, a mathematician looking at this say that, okay, let me now think about this problem, which is a little bit harder. Okay. By the way, this mathematician is not absent-minded. Whenever you see this relation, it reminds you of something very famous. Can you tell me what? Yes? For what? No, let us not jump to that point, yes. But now a very, very famous one. Yes? Pythagoras theorem. Okay, so the mathematician is really not absent-minded if you want to think about this. Okay? So now, let us say I have this equation, and I want to ask you the same question. Okay? Can you find a triple of numbers coming from this long list that satisfies that equation now? Of course, that equation is a little bit harder than that one, yes? This is first power, this is second power, so usually second power problems are harder than the first one problems, okay? So, but can you find a triple for me? Yes?
3, 4, and 5.
These are very famous Pythagorean numbers, yes? So 3, 4, and 5. So this is a problem in discrete mathematics. So you see there are no prerequisites that much. So I ask you, can you find that? And you found it. So I can ask this question. Is there any triple of integers that satisfy this equation? The answer is yes. And if I ask you more, can you give me an example? You just gave it. Because that's the one problem, okay? So this is E-level question, you solve it, okay? And then the next question that I ask is that how many triples do you think I can find? So here, the answer was very trivial. You told me that there are infinitely many ways that I can adjust these three variables so that x plus y becomes equal to z. Yes or no? Okay, now I want to ask the same question here. It is a little bit harder, okay? One of them you see in the list. Why this is working? Because 3 to power 2 is 9, 4 to power 2 is 16. If I add them, it becomes 25. And if I put 5 here and raise it to power 2, it becomes 25 as well. So that is really working. But how many of these numbers? I cannot follow the same strategy. You see, the question is the same. Yes, how many triples are there? But I cannot use the same strategy as used before at all. Because what was my method here? I told you choose two of them, any one that you want, add them, it gives you the third number. But why I cannot use the same strategy here? For example, can I say choose any two numbers that you like? Let us say x is equal to 1 and y is equal to 2. Okay? And then, do you think I can get the third one? No. Why? Because if I calculate x squared plus y squared this time, it becomes 1 to power 2 plus 2 to power 2, which is 5. And then, if I want to make it equal to z squared, what should I choose for z? A square root of 5. But the square root of 5 is not in my list. Is that clear? So, the problems are very similar. Yes, the only difference is that the power is 2, and I am asking you exact same question. How many triples you can find here? Okay? If you say infinitely many, the method that I used here will not work there. Okay? But let me rephrase my question. How many triples you can find if I don't have this limitation that these numbers should be integers? These numbers could be any numbers. The question is that if x, y, and z are any numbers, okay, then how many triples you expect here? Yes? Infinitely many. Do you think the same method that argued here will still work in this case? In this case, yes. Yes? So it means that if I choose x, y, and z to be real, then I can follow the same logic. Yes? Because I tell you, choose any two numbers that you like, calculate this one, take the square root of that number, it gives you the third number. But I hope that you understand, when I limit myself to the set of integers, this is not working. Okay? Now, my question for you is that, okay, let us go back to the original problem. So I have this equation. I want to have x, y, and z chosen from this long list. And I am asking you, how many triples do you think I can manage to find that fits that equation? And then why? Today's lesson is not a very formal lesson. I want you to see that what is the difficulty in discrete mathematics. These two questions are very similar, but the arguments are completely different, as you will see hopefully. But still, if I solve that problem for you, it is a matter of seconds to understand the solution. But because the solution is so simple, it doesn't mean that finding the solution is also simple. Yes, so this is the way that you need to think in this course. Okay, so if you can solve the problem, you cannot solve the second one, you don't feel that you didn't learn anything. That's the nature of this course. Okay, so can you tell me how many triples you expect? And then you need to defend yourself. Okay?
There are infinitely many because you can just multiply every number in that triple with any integer, and that will still apply.
Yeah. So that is the rule. So he is saying that, do you agree that this triple works? Yes. By putting them here, we see that it really works. And then I would say this is important. In discrete mathematics, you need to write the sentence in a proper way. So I would say let n be an integer. This is needed to be written down, yes? Then let, for example, x be equals to 3n, y be equals to 4n, and z be equals to 5n. We have, what do we have? X squared plus y squared is equal. X is 3n squared, y squared is 4n squared, but you know how to do this simple algebra. 3n squared is 9n squared. This is 16n squared. So hopefully you know that this is 25n squared. But 25n squared can be written as 5n to the power of 2. But what was the name of 5n? It was z squared. Okay? This is the way that I expect you to write. But of course, I want you to understand as well. So what I am saying is that you choose an integer. How many choices you have? Infinitely many. You choose any integer that you like and take that integer and multiply it by these three numbers. Okay? You produce a new triple. Yes? For example, if you choose 3, multiply this by 3, it gives you 9. Multiply this by 3, it gives you 12. Multiply this by 3, it gives you 15. If I choose, for example, I don't know, 2, I multiply this by 2, it gives me 6. This mod 2 is 8, and this is 10. Okay? So it is clear that I have infinitely many choices for my integer. When I chose that, I take that one and multiply it in these numbers. I get 3 new numbers, 3n, 4n, and 5n. And I showed to you that regardless of my choice for n, x squared plus y squared is equal to z squared. Is that clear? Yes or no? Are you with me or not?
Yes.
Okay, so it means that I was able to show that there are infinitely many triples coming from this list that satisfy this equation. Okay, and then if you see, these two problems are very similar, but if you could have solved this problem in principle, there is no guarantee that you can also solve this problem, because what you argue here is different from what argued before. More or less totally different. Is that clear? Yes or no? Okay, so that's the type of problems that you have to expect in this course. Okay, and by the way, the prerequisite here was just algebra at the level of Math 1C, because this is the algebra that I have done. This 1 to power 2, this is 9 on a squared, and this is 16 on a squared, and I just add them. Yes?
Was this a proof that it will always be infinite? Because like last lesson you said to prove something, you can't just give an example, you need to like prove it in some way.
No, that's not an example. That's important to understand. The question was this: how many triples of integers you can find that fits into this equation? So I have a claim. My claim is that infinitely many. Then I have to have an argue, because when it is infinitely many, it doesn't matter if I bring 1,000 examples for you, because I want to show that there are infinitely many. So I cannot bring examples to show you. So I have to have an argument to be able to convince you that there are infinitely many. But now what I told you that, first of all, do you agree this triple works? You say yes. Now I say that, okay, keep this triple and choose any number from this that you like. How many choices you have? Infinitely many. But you pick one. But you have infinitely many choices. Multiply that number that you picked by this triple, it generates a new triple. And I prove to you that this new triple, regardless of the value you choose for n, still works. So this means there are infinitely many. Is that clear? So this is the line of reasoning. Okay? Okay. But as I told you, if you are a mathematician and solve this problem, as far as you put your head on the pillow, you will start making a new problem for you. Okay? So the problem is that what is the natural next question comes if you're if you are a mathematician or if you have that way? Yeah.
X cubed.
Yeah. Isn't it natural? Yeah, so it means that this is the simplest way if you want to keep yourself busy. So if you have been busy one day for this, one day for this, you can keep yourself busy by asking yourself the same question for this equation. Okay? So x cubed plus y cubed is equal to z cubed. Yes. Again, let me test your understanding. If I relax that condition, so let us say that instead of having these restrictions that x, y, and z are coming from z, this set, let us relax that condition and I say that x, y, and z are real numbers. Okay? And I ask you the same question. How many triples, x, y, and z, coming from the set of real numbers one can find so that that triple satisfies this equation? What? Let me everyone think about it. Yes? None? My question is about, okay, none. How many? So you said infinitely many, you said none. There's no big difference, yes? None, infinitely many. But which one is correct? Or you have something in the middle? Yes? Can you defend yourself?
If you have all the numbers, you can make up a lot of different.
This what you are saying is your intuition. Okay? It's a good thing in mathematics you develop your own intuition about the problem. But of course, at the end of the day, you cannot trust just your intuition. You have to have an argument. Yes? So that's exactly one thing I want to mention. If you believe what I said is true, you cannot bring just examples for me. You have to have an argument why it is working. But if you want to say no, then bringing an example that's showing me it does not work is enough. We will talk a little bit about these things. But can you defend yourself? So your claim is that there are infinitely many except that's exactly the hard part of this course. Because if I give you this in the exam, even if you say infinitely many, and even if infinitely many is right, but you have to write why. Okay? So not only you need to be able to defend yourself orally, but you have to improve your writing skills in mathematics as well. Okay? So can you defend yourself?
I can try.
Yes? What's your name?
Discipline.
Yes?
I guess it's possible to do a similar thing with the
Yes?
x.
Yeah, can you just repeat it because we want to learn?
So if you take if you pick a number for x and y.
Okay, so you would say that this is important by the way, because I want you to learn how to write in the exam, yes? So you say let x and y be real numbers. Okay? Then, what is your suggestion for the z?
It's be the sum of x and y. Like, no, I'm sorry. The sum of x cubed and r cubed.
No, that is z cubed. I'm asking you about z, because if you say yes, you need to give me one x, one y, and one z that works. I would say that let us x and y be these two numbers. So what is your z then?
The sum of x and y cubed.
Exactly. No, the sum of x cubed, y cubed. Yes? Yeah, so this is exactly because you want to find your z, yes? So I would say that let x and y be real numbers, or you can say be arbitrary real numbers. Then the triple x, y, and the third root of x cubed plus y cubed satisfies this equation. Yes? Is that clear? Because do you agree that this triple satisfies this equation? Why? Because if you put x here, it becomes x cubed. If you put y here, it becomes y cubed. Instead of z, if you put here, this power of 3 will kill this third root, and then you will have x cubed plus y cubed again. So this triple really satisfies this equation. Okay? But how many of these triples you can choose? Infinitely many. Because did I say anything about x and y? No, except for that they are real. How many choices I have for x and y? Infinitely many. So for every x and y, for example, let me just give you, if someone chooses x to be 1 and y to be 2, and then that person should choose z to be the third root of 1 to power 3 plus 2 to power 3, which is the third root of 9. Yes? So 1, 2, third root of 9 is one triple that works in this equation. But do you see there is nothing special about 1 and 2? I can choose 1 and 2 whatever numbers I want to and then calculate z out of it and it will work. Is that clear? So there are infinitely many. Okay, but now again, let me ask the same question here. How many triples of integers do you think we will have here? Okay. Now I go back. I want to give me numbers only from this list that satisfies this equation. So for this one, this was easy to immediately find, and using that we constructed infinitely many more. But for this one, can you, of course, the calculation might be harder because the power is 3, but I don't know if you have calculator, probably you can use it. But can you give me a triple coming from this list now that satisfies this equation? If working with negative numbers is hard, forget about negative numbers. Just work with positive numbers. Of course, you can also work with negative because you can choose two of them, one of them positive, the other one negative. They will be subtracted because the power is odd. Okay. So what's your opinion? Could you find a triple for me? Yes?
X is 0, y is 2, and z is 8.
X is 0. Y is
2.
2. And Z is?
So I'm just a little confused.
No, it's not confused. I think it's right.
Yeah, but but I just forgot if it was 64 or 8.
No, z is also 2.
Is it?
Yes? Because 0 to power 3 is 0, 2 to power 3 is 8, 2 to power 3 is 8. Yes? So now, actually I wasn't very careful when I asked my question. That's true. So he chose a list, a number, 3 numbers from that list that satisfies this equation. Yes? So that is not that hard. Yes? Is that clear? Okay, so this works, but let us say that we exclude 0 now. Okay, but this was, I expecting actually you should say this because it was not that hard, you know. Even you can choose 1 and 1. But let us try to ignore the negative ones and zeros. Okay? Only positive ones. So what do you think now? Because in principle, one of them you can choose 0 and you choose y and z to be the same. Yes, because if you choose 0, then, by the way, how many solutions you have in that case? So if the same question, how many triples you can find if there is no limitations? Of course, there are infinitely many again, because you can choose x always to be 0, choose y 1, z also becomes 1, choose y 2, z also becomes 2. Okay, but let us now exclude the negative ones and 0. Okay, then so I just want you to feel this one, because you are in a uncertain situation now. Okay, if I take the only positive ones, 1, 2, 3, 4, etc., it is not immediately clear you cannot find a triple. It's not that easy to find the triple. Yes? Or might be you say that, okay, time is not enough. If I go home and I have my computer in front of me, I do some trial and error and try to find the answer. Okay? I want you to feel that. So some of you might think that you will be able to find it. Some of you might think that you will not be able to find it, or you want to defend your argument or whatever. But the point is that it is being proven by mathematicians that you cannot find any triple coming from positive numbers that satisfies this equation. And I want you to feel it's extremely big claim. You see, it's a very big claim. Because in potentially, how many choices we have to do trial and error? Infinitely many. And even if you have supercomputers, supercomputers, infinitely many takes infinitely many time, even for supercomputers. Okay? So it is not possible to start calculating things, because even if you calculate billions of billions triples, and using your supercomputer you see it does not work, you cannot still say that, okay, I am relieved it will not work. Okay? Because you haven't checked every case. This is extremely important. So when you say you cannot find, first of all, I want you to see that this is a very big claim. It tells you, it relieves you somehow, because you say that, okay, I follow the logic. Yes, you are right. If I follow this logic, I understand there are no triples. Okay? And it was already solved before, but I told you that mathematicians start, when they solve that problem, then they realize there are no solutions, they want to go higher and higher. Okay, so the most general problem of this type was this theorem, which was, let me not call it theorem, it is called Fermat's last theorem. Okay, the claim is this: if I choose an arbitrary power, not just 1, 2, 3, an arbitrary power, but the power be greater than or equal to 3. N, this symbol means n belongs to the natural numbers. Natural numbers are 1, 2, 3, etc. Okay? And n is greater than or equal to 3. Fermat was actually a lawyer. Okay? He was living in 17th century. And he was doing a lot of good mathematics, actually. A historian of mathematicians actually found the book that he was studying, or he has written, I don't remember exactly. And he has mentioned this, that for any natural number greater than or equal to 3, it is impossible to find a triple x, y, and z coming from the set of natural numbers that satisfies this equation. Okay? It is the most general argument. And he wrote, unfortunately, I found a marvelous proof for this claim, an argument, claim, that does not fit into the margin of this book. Okay? And then nobody actually could find that proof. Okay? So it was stated around 16, if I don't remember exact date, but that was more or less the same date, 1692. And then it was eventually solved, this I'm sure, 1993. So it took nearly 300 years, yes? So he claimed this, that not for this case, for the power 4, for power 5, for power 6, and onwards, no one can find the triple of natural numbers that satisfies this equation. I want you to feel that this is still a big claim. Yes? Okay. And then it took mathematicians 300 years to finally prove that he was right. Okay? So he was right. But before 1993, this was an open problem. An open problem in mathematics is somehow called a conjecture. I want you to know these words, okay? So conjecture is a problem in mathematics that seems to be correct, but there is no proof for it yet. Okay? And by the way, some mathematicians try to refute it, especially in the 21st century that we had, in 20th century, we had powers of computers. They were trying to find a triple that works. Okay? Because if a primary school kid, by accident or coincidence or whatever, they can come up with a triple that works for some n greater than or equal to 3, it means that the effort of those professional mathematicians has spoiled, actually, because they found an example that shows that Fermat was wrong. Bringing an example to refute a statement has also a name in mathematics. I want you to know that. So counterexample. So I want you to learn these words. Of course, I will not ask you to define them, but I might use them when I'm teaching. So I want you to know these words. So conjecture is actually a statement that seems to be true, but that we don't have any proof for it yet. That's called conjecture. So conjecture is more or less an open problem in mathematics. As soon as it is proved and confirmed, then the name conjecture turns into what? You know? Theorem. Yes? So theorem is a statement which we have a proof for it. So then we can rely on it. But as far as it's a conjecture, we still don't know if it is true or false. And what is the meaning of a counterexample? It means that you bring that example that shows that an argument in general is not true. So if you want to refute a general statement, you really don't need to look for an argument. You just need to look for an example that shows that it doesn't work. And that is called a counterexample. Okay. And then let me just give you a little bit of history about this. So you know that in science we have Nobel Prize, but in mathematics we don't have Nobel Prize. The highest prize that we have is called Fields Medal. I don't know, there is a rumor that Nobel was a Swedish inventor of the dynamics, yes? So it's a rumor, it's true or not, I don't know. He said that, okay, his wife was cheating on him, and the person who was cheating was a mathematician. So he said that, okay, don't give my prize to mathematicians. This it is a rule, it's a rumor or not, I don't know. But anyway, the highest honor that you can have in the mathematics world is to win the Fields Medal. By the way, it's nearly 14,000 Canadian dollars compared to 1.2 million US dollars. Okay, so I mean the money point of view, that's nothing, but that's the highest prestige. But there's a limitation, unfortunately, for that. You can only get it if you are below 40. In Nobel Prize, we don't have any age limitation. Okay, and then what happened? So he was able, Sir Andrew Wiles, from Princeton University, finally was able to prove this, and the proof was 250 pages, more or less. So it was not that easy. I don't know. His claim was that he couldn't fit it in that margin, but it's much, much bigger than that. So it was 250 pages. Whenever you discover something like this, you have a conference, you present what you have seen, what you have done, and then another brilliant mathematician was able to find a very small flaw in the proof. Okay? So, and then they discussed, and then he said that probably we will be able to solve that flaw. Okay, so they had money, so they hired postdocs and PhD students to work on this together, and they finally solved the problem after 2 months and a half or something. But after that, he passed age 40. So he was very close to age 40, but at least because of that 2 months, he passed that age, and he didn't get that Fields Medal, because this is probably the most ancient problem left open for 300 years, and this guy was able finally to solve the problem. And there is a documentary on that on BBC. I really recommend you to watch it. I think it's BBC4, the BBC4 channel. So it's a very nice documentary, and he describes what he was feeling about this theorem. He said that when he was 10 or 11 or something like that, he found a book in the library that it was written the same thing that I mentioned to you. He said that as a 10-year-old student, I was able to understand the problem because the problem was easy, yes? You cannot find integers that fit this equation. Okay? And then it was written that this is 300 years that mathematicians have worked on it and couldn't solve the problem. So this is the nature of discrete mathematics. A statement of the problem was extremely simple. Every one of you could understand. Even I could tell it to Math 1C students. But solving the problem took 300 years. Okay? Okay, and he said that after I became math professor, I don't know, at the age of 30 or something, I realized I will be able to solve this problem. Yes, because of the progress that other mathematicians have done. So he said that, okay, I said goodbye to my family. I went to the top store. I was working 10 hours, 15 hours per day for 10 years to be able to solve the problem. And he describes that. He just started crying. He cannot talk about it. Okay, so he becomes very emotional. So I want to just try to see if I can find the link. I will put it in the Google Classroom. It's good to see these things. Okay. So this is what I want to say. Statements of the problems are extremely simple, but there is no guarantee that the solutions are also simple. Yes, they might be extremely, extremely hard. And you also learned about the word conjecture, counterexample, and theorems. Any questions so far? Yes? By the way, so before that, we had proofs for this. I mean, that's also, I think, another mathematician more or less immediately came up with a solution for this, that there are no triples. So for 3, 4, 5, 6, 7, up to 9, I think it was proven, okay? But for the general case that for any n, we cannot find such a triple, it wasn't been solved until 1993. Okay, any questions? Yes.
But the example you wrote up there works when you put 0.
No, not 0. That's what I'm saying. Just go to the natural numbers. Yes. If you want, you can search it. Might be I have a little bit minor difference, but I think this is the case. So Fermat's last theorem, if you just Google it, you can find. We can do it now. The reason that they say positive integers because we have two school of thoughts. In American school of mathematics, the natural numbers starts from 1, 1, 2, 3, etc. And in European system, they start from 0. So they say natural numbers 0, 1, 2, 3. Okay? So to get rid of this confusion, whenever you want to say from 1, they say positive integers. Why? Because 0 is positive or negative? Neither. So 0 is neither a positive nor negative. It's good also to know. I will also use it. So non-negative, it doesn't mean positive. Yes? When you say positive, it means strictly greater than 0. Okay, 0 is not acceptable. But when you say non-negative, it means it is not the case that it is negative. It means greater than or equal to 0. Okay? So these words, it's good to know about it. Okay. Of course, he told that there were no way for Fermat to have the proof. Might be he had a mistake. He thought that he had a proof there. And the reason is that Fermat, even though he was clever, but he made some very stupid mistakes sometimes. For example, this is also part of the lesson. I'm not just teaching you history. Okay, I'm using history to motivate you. So Fermat claimed also that this formula only generates prime numbers. Yes? So you know prime number is, what the prime number is? A prime number is a number greater than 1, natural number greater than 1, which is divisible by itself only and 1. Yes? Okay? So a prime number is a natural number greater than 1. Mathematicians have decided to exclude 1 from being a prime. Okay? So that it is only divisible by itself and 1. Okay? He claimed, and you know that we haven't discovered any formula that generates all the prime numbers. Okay? If you have that formula, you will win $1 million US. Yes? So, but he was claiming that this formula only generates prime number. He was not claiming that it generates all prime numbers, but he was claiming that this formula generates prime numbers only. So for example, if I put n equals to 1, what is the answer? By the way, do you know that if I have a sequence of powers, what does it mean? So if you see a to power b, if you put parentheses here to power c, it means a to the power of bc. But if you write a, b to the c without any parentheses, it means that the priority by convention is given to this. So if I ask you to calculate 2 to the power of 2 to the power of 1 plus 1 without any pairs of brackets around anything, it means that you have to calculate this power first. So 2 to power 1 is 2, then you put this one, it becomes 4 plus 1 is 5. Yes, 5 is a prime number. And then 2 to the power of 2 to the power of 2 plus 1. 2 to the power of 2 is 4, so this becomes 2 to the power of 4 plus 1, it becomes 17. Yes, that's also correct. And then 2 to the power of 2 to the power of 3 plus 1. What is the answer to this? 2 to the power of 3 is 8, so 2 to the power 8 plus 1. 2 to the power 8 is 256, this is 257. If you check it, that's also prime. Okay? I don't know, 2 to the power of 2 to the power 4 plus 1, it's 2 to the power of 16 plus 1, I don't have it in my head. But the point is that even though this problem is not that hard, I don't know why he missed it, this is also a prime, if you calculate that. But when you calculate it for number 5, which is 2 to the power of 2 to the power of 5 plus 1, which is 2 to the power 5 is 32 plus 1, it turns out that this number is not a prime number. And so, because Fermat had a bad reputation to saying good things and nonsense things, so people don't that much trust about what he wrote in that margin, okay? Because this is very easy to check. So let us say we go here, so ChatGPT now, okay? So ChatGPT probably calculates the mathematical problem using Wolfram Alpha, okay? So for example, if I remember correctly, the syntax of course, you know that the point is that I can write is 73 prime number. So you can type on it, okay. Say yes, 73 is a prime number, okay? But let me use the syntax of the language. The syntax of the language is prime. Let me see if I, let me see. Just a moment, please. Let me see if it's being recorded here. So I don't know what happens. Okay, so let me use my account. Okay, it doesn't matter. So, okay, so here, for example, the syntax is that you write prime and then you put a capital Q and put your number there. For example, I put 8. Okay, so is 8 a prime number? Of course, you know that it is not. So let me check it. So you see that is 8 a prime number? No, it is not. Yes? So this is the syntax you use. For example, let me calculate that number. It is 2 to the power of 16, which we know it is, plus 1. Okay? And then let me ask this if this is a prime number here. Yes? It is asking, is this number a prime? The answer is yes, it is a prime number. Okay? But now if I go to 32, Fermat was thinking that this should also be a prime number. Yes, but if you calculate that one, is this a prime number? No, it is not a prime number. So it was not that hard, but probably for Fermat was hard to factorize this to see that this is not, because they don't have access to computers, yes? Okay, a better example I can show you, let me tell you this. Another guy actually said that this generates a prime number. Okay, let us check. For example, if I put n equals to 1, it gives me 43. Yes, that's correct. If I put 2, it becomes 4 plus 2, 6, 47. That's also correct. I don't know, 3, 9 plus 3, 12, 53. Yeah, that's also correct. So he claimed that this also generates prime number. Okay, let us check it here on Wolfram Alpha, yes? Okay, so but I want to generate that one if I remember the syntax of this language. So I generate a table. Can you see that? Yes. Of n to the power of 2 plus n plus 1, and then let me limit n to 1 up to 39. Okay? Okay, so if I generate these numbers, I am taking n from 1 up to 39. So if you put 1, it generates 3. Oh, sorry, this is not 1, this is 41. Okay, so you see, I change n with 1, the answer is 43. I change n with 2, the answer is 47. And if you continue this list, you will see that. Okay? Okay, but now I want to apply the function prime onto the table. Okay, so you don't need to learn these things. I'm just trying to, if I remember, the syntax is this syntax, I think. So this will apply this function on every element in that table. Yes? And you see, it is true, true, true. It means that I am asking, is the first element a prime number? It is true, yes. The second element is a prime number, yes. So you see that it is a prime number, yes? Okay, but now let me change it to 40. Instead of having it up to 39, let me make it up to 40. What happens? You see the last one is false. So this formula was generating prime numbers. So if you check the first one, the second one, the third one, I don't know, the 30th one, 39th one, it was working. Then suddenly it stops working when you put 40. Yes? So this is extremely important to see that when you want to claim or you want to convince yourself, bringing a lot of examples is not enough. There are examples that it works until the number 1 million or something. Then suddenly after that there is a counterexample. Okay? So this is extremely important. don't delude yourself into just checking some few number of cases. Few number of cases sometimes becomes 1 million cases. It works and then suddenly stops working. Okay? So this is important to understand that. By the way, it was not hard at all. So that would be a good problem for the exam in this course. For example, I could say that, do you think that this formula generates prime numbers? Okay? Motivate your answer. Well, how do you do that? And the calculator is not allowed in that part. Oh, that's what I'm saying. That's a very typical exam question, yes? I give you this formula and I ask you, do you think that this formula generates only prime numbers? Motivate your answer. And I give you this question in that part that you don't have access to computers or calculators. How do you answer the question?
Just come up with a counter example.
Okay, but you don't have calculator with you. Exactly, you're right. First of all, you need to convince yourself if it is true or false. That's also something that you need to decide. Okay? Let us say you understand and you have the knowledge that no formula is being discovered, so you know that you are going to find a counterexample. That's what I'm saying. Finding a counterexample is not necessarily easy or trivial. Okay? Okay, so how do you answer this in the exam? So you see, when I solve the problem, it becomes extremely simple. But that's the nature of this course. I want you to understand that. So everyone agrees. We want to find a counterexample. We want to motivate the teacher, the examiner, so that for this number at least, it does not generate a prime number. And the problem is in that part that you're not allowed to use the calculator. By the way, by calculator, it's also not that easy. Yes? For example, here, if I show you this, if you don't have programming language, so let me take this off. Okay, so let me calculate this number. So for example, you need to know why these numbers are not prime numbers. Why the last number is not a prime number. Okay, so how do you do that? Even if you have calculator, you have to divide by a lot of numbers to see if it's not divisible or not. Or you have to be creative, which is extremely simple here. Yes?
What if you like take out the n, so just n times n plus 1 plus 40 plus 1?
Okay, then what? It is not a product anymore. But you are close. The idea is what you said. So in the exam you would say, no, this formula does not generate only prime numbers. Since, for example, if n is 41, then, okay, can you see why 41 is so simple to understand? Then n squared plus n plus 41 is equal to 41 squared plus 41 plus 41. Do you agree? Yes? But I can factor a 41 out. So this becomes 41. This becomes 1. This also becomes 1. And then this becomes 41 multiplied by 43. So this number, whatever it is 41 times 43, but it cannot be a prime number because it's the product of two numbers. Is that clear? Do you understand or no? So you see, the claim was that this formula generates only prime numbers, and it really did up to 39, step 39. But you want to say, no, this is not the case that it only generates prime number, and you don't have calculator available. But it was not that hard. Might be it was hard for you because you don't have that much experience, but if you choose n equals to 41, what will happen? This becomes this number, but instead of suffering and calculating this and proving that that's not a prime number, I can take the initiative and factor 41 out, then I immediately realize this number is 41 times 43, and I don't need to know what is this number. What is important is that this number is written as a product of two numbers, so this number cannot be a prime number. So you see, again, the solution is very simple, but coming the solution to mind is not that simple. So you have to train yourself. And by practice, by the way, this is not something that you need to freak out, okay? So you will learn that by practicing, okay? But it's not that hard. But what about 40? By the way, here, I choose 40 and it was false. Can you see why for 40 it's also false? Because if I replace, 41 was easier to understand. Because when I chose 41, then I was able to pull out 41 and see the product. Yes? But if I choose 40, what happens? Do you immediately see that this is not a prime number? For example, in the exam, I can give you this and ask you show that this is not a prime number. Calculator is not allowed. Okay? So how do you convince me that's not a prime number? Calculator is not allowed, okay? So you see, now we solved that problem, okay? I gave you a very, very similar problem. But might be you have to change the way you think a little bit or very much. So this is the nature of this course. So what we can do here? Yes?
Just do 40, turn 40 to the power of 2 to 40 times 40. And
Okay, so you say that you write 40 times 40
yes,
instead of this one, and then you have a 40 here, the 41 here, okay, then?
okay, and then factorize 40 times 40 plus 40 to 40 times.
Yes, so now you factor a 40 out from these
Yes.
two. Yes? So it becomes 40. What is left? 40 plus 1. And then at the end you have 41.
Yes.
But then you get lucky because 40 plus 1 becomes what? It becomes 40 times 41 and then another 41. Then what?
Then you just
Then I can factor the 41 out.
yes.
So it becomes 41, 40 plus 1. But then coincidentally this becomes again 41. So it is 41 times 41. It's not a prime number. Okay? So you see, we are just inventing problems, yes? When we solve the first problem, you invent a new problem. You invent a new problem. So that's the idea. So for 41, because all of them are 41, it was easy to understand that I can pull a 41 out and write it as a product. But when I choose 40, it was not that obvious as before, because 40 and 40 is just common between these two, and 41 is something else. So then either you have to give up, or you need to find a new way. Well, the new way is that, okay, I cannot do as I did before, so what else I can do? And Samir actually told what to do, yes? So we factor a 40 out from here, okay? And then I have a 41, and I get lucky because this becomes 41, then I can pull 41 out again. That's a coincidence, you know? This is something you don't expect, you know? This is like a, how do you say, disposal towel or something. You just use the solution, throw it away. This only works for that solution, yes? So, okay. So I want to stop here. So this is one example that shows you that just checking some few cases, it is not enough at all to jump and conclude that something in general is true. Okay? And you also learned about a little bit of history and the problems you should expect. So this nature will be for this course, more or less everywhere. Might be except for set theory. Yeah, in set theory, we have some kind of rules we can follow, but other parts of discrete mathematics have this nature. Yes?
Would this problem be possible if we didn't know that the conjecture doesn't is false?
No, which conjecture?
Because we knew it from the beginning that it won't work. This we did right.
No. When I say this in the exam, you cannot say because I have some enough knowledge, I know that no formula has been invented. By the way, the formula that I am sure is still it's not a conjecture. No one has come up with a closed formula that generates all prime sequences. Okay, so you cannot use the history of mathematics to write something.
So how would I know that this one doesn't work from the beginning?
No, I tell you, yes. No, that's also another problem. At this level, you need to decide for yourself. But no one asks you motivate why you say no. You can say, I am so genius, I understand that's no, and that's the solution. No one in mathematics asks you, how did you come up with the feeling you want to say no? That is exactly the torture that people are being done in mathematics, because if there is a problem, still we don't know, is it true or false? If it is true, we have to go this way to prove it. If this is false, we have to go in exactly opposite way to find a counterexample. Okay, so that's the type of problem. But of course, this is elementary course in high school. Okay, I don't want to torture you, but I mean, this problem you should expect. This is not higher than the level of the problems in the book. Is that clear? Okay. Any questions? Okay, so here